This is the first part of section 1.2 on finding limits graphically and numerically. By the end of this lesson, you want to be able to understand what a limit is and how to find a limit using a graph and how to find a limit using a table of values. That's called numerically. Let's start with the verbal definition of what a limit is. If f of x becomes arbitrarily close to a single number L, as x approaches c, some number, from either side, let's think of that as both sides, then the limit of f of x as x approaches c is L. This is often the way we say it verbally. The limit of f of x as x approaches c is L. Or as x approaches c, the limit of f of x is L, where c and L are some real numbers. Now, the most important thing that you want to take from this is that numbers are being approached, not necessarily reached. So let's make this really important note, bold it, star it, that the limit is all about where the function is going, not where it gets. It might not ever get anywhere. It's where is the function headed? Where is it going? Not where it arrives, because it might never arrive somewhere, anywhere. So we're going to look at three different ways. We're going to look at the graphical way to tell what a limit is. So graphically, that just means refer to a graph. Such as this one that's sketched here. So what you want to see is the c value is an x value. Here's our x-axis. L is referring to a value along the y-axis. And what we want to look at, so in this case, c we can call 2, and L we can call 3. But the C and the L there are for the purpose of understanding a little bit more the general verbal description that's written up here. So we have our function here. Let's call that f of x, so that later when we write it with symbols, we know what we're referring to. And what we want to see is, if we are writing something about this graph, about its limit, we would write the limit as x approaches 2, instead of c, using this picture we can call it 2, of this function, we're calling it f of x, equals 3. Looking at this graph, why is that happening? So here's what we're looking for. As we get closer, looking left and right, that's location, to the x value 2. So coming from the left side of 2, I'm looking at the graph, and here I am coming closer to where x is 2, or coming from the right side of 2, but going up to where the function is and coming towards where x is 2. I want to look and see where are the y values headed, and what I see on this graph is that the y values are headed to 3. So that's why we say the limit as x approaches 2 of our function f of x is 3. Now finding a limit analytically is what we're going to focus on in section 1.3. So we're going to discuss that more later. But analytically means that we are going to use more algebraic rules. Okay, but that's for a different lesson. Let's talk about what it means numerically. That means looking at the numbers that you plug in at a graph, or in this case, looking at a table of values. So what you're going to see in a table of values is as you bring your x values closer and closer to some number. So back to this graph, we were looking at approaching 2. So I'm going to put 2 in the middle of our table right here. And I'm going to say, looking at what's happening from the left of 2, from the left, so numbers smaller than 2, such as 1.97. But you can get closer. 1.98, but you can get closer. 1.99, we're getting closer to 2 coming from the left. What is happening to the y values? If you plug this function into your calculator, you'll see the y values are doing this: 2.5, 2.6, 2.9. Now, if you were to plug in 2, what you might see is that there's an error. Nothing can go there. If you reference back to the graph, you see a hole. There is no y value for the x value too. Now, coming from the right, we want to pick values of the x that are close to 2, but on the right. So maybe you start with something just bigger than 2 slightly, like 2.1, but heck, you can get closer, 2.01. You can get even closer than that, like 2.001. Plugging those in your calculator, you might get something like 3.8, and then 3.4, and then 3.1. So you ask yourself, what does it look like our function values are approaching as our x values approach 2? If we plug in 2, we might not necessarily see it, but where does it look like the numbers are headed? And it looks like they are headed closer to 3, like we said in the graph and like we said when we wrote it with the symbols. Now, we're going to talk about these symbols later in a different section, but just to give you a little introduction, coming from the left, we would write the limit as x approaches 2 with a little negative symbol, meaning coming from the more negative side of that value of f of x. Or on this side, we would say coming from the right would look like this, the limit as x approaches 2 from the right. What is the limit of the function? Let's look at a couple of example problems. If you have a graphing calculator, it would be great at this time for you to plug in this function right here. This function f of x equals, or y equals, or h of x equals 2x squared plus 7x plus 3 over the quantity x plus 3. Now, we all know that when there's a denominator, something fishy could happen. We don't want our denominator ever to equal 0 because we know we can't divide by 0. So let's take a look at what happens when we write x plus 3 equals 0, since we know we never want that to happen, and we solve it. We get x equals negative 3. That means in our graph, something fishy is going on. There might be an asymptote, a vertical asymptote, or a hole. Go ahead and take a second to plug it into your calculator. You can pause this video if you need to. Then you can plot the points that you get in the table of values from your calculator. For example, what I see in mine is that when I plug in negative 2, I get negative 3. When I plug in negative 1, I get negative 1. When I plug in 0, I get 1. 1, I get 3. So it looks like it's creating a straight line. In fact, if you can extend your view to something even larger than what I have, you can see down farther this way. Now, what I can't see is what's happening, but if it's linear, what we know is that it's going to continue in the same behavior going this way. Now, what's going to happen at negative 3, though? Well, our calculator shows that it looks like it just goes straight through, but we know that's not actually happening if we look at our table of values. In fact, it is a hole that's there. Now, again, referring to our table of values, what we're ultimately trying to figure out is what is the limit of this function as x approaches negative 3. If we plug in negative 3, we don't see anything. Maybe we see error. So we want to plug in values that get really close to negative 3, coming from the left and coming from the right. These are values that I chose from the left, negative 3.1, negative 3.01, negative 3.001. I got negative 5.2, negative 5.02, negative 5.002. Coming from the right, I chose values slightly bigger than negative 3, starting with negative 2.9, but getting even closer, negative 2.99, and then really, really close, negative 2.999. Here's what I got, negative 4.8, negative 4.98, negative 4.998. Coming from the left, it looks like the y values are getting closer to negative 5. Coming from the right, it looks like the y values are getting closer to negative 5. So looking at the graph, again, as I come from the left of negative 3, my function looks like it's getting closer to negative 5. Coming from the right of negative 3, it looks like my function is getting closer to negative 5. Therefore, I'm going to write the limit as x approaches negative 3 of 2x squared plus 7x plus 3 over x plus 3 equals negative 5. Now I don't want to write f of x right here because f of x hasn't been defined as anything yet, unless maybe I have defined it in this table here. Then I can say that it's the limit of f of x. Using words, I can say as x approaches negative 3, f of x approaches negative 5. The limit is about where the function is going. In the previous example, we found the limit as x approaches negative 3 is negative 5. However, f of negative 3, the function value at negative 3, does not exist. Same deal with that picture example here. In this picture, I called this f of x, f of c, or rather we called it 2, f of 2, does not exist. Does not exist. That's the function value. The limit can exist even when the function value does not. Because remember, the function, we're looking at where it's going. The limit is where the function is going. Not where it gets, but where the function is going.